and these, like each of these individually you do well, or the worst of those you do well. And this seems like much more in line with like you would want covariate balancing. That seems like it would make you do better at that. So it feels like the trade-off would be different there. So I'm curious about that kind of classical notion of robustness versus the notion of robustness you've introduced, which is average over all of these like covariate groups you could have at once.
Yeah, so let me just clarify our definition. It has nothing to do with covariates. It means that, you know, I'm going to run a randomized experiment. There are many possible potential outcomes that could be true. I don't know which ones. But within some ball, I've just defined an L2 ball. Within some ball, I want to make sure that my mean square error for everything in this ball is not too large. And I should make a design that satisfies that. That's what a robust design is for us. I admit the term robust is like overloaded. But so our definition of robustness has nothing to do with covariates necessarily. Now, you asked a question, which was, what about if you want to estimate treatment effects, you know, on populations of people in your study here, not just on all. So I wrote our, you know, our estimate of interest is the average treatment effect over everyone in the study. If you wanted to do multiple estimates, you know, at the same time, that's something that I do not know as well, but I know that people think about that. So I really have no good answer besides that's not what we're doing. That's a very cool thing. And I would presume that covariate balancing would be a good thing, but I don't know like in what ways, like rigorously, I don't know that.
Cool, thanks a lot.
Arnab, just a question to Arnab. So you're using very large interventions as S, that are like linear size.
Right.
As you scale that down, do you just have, but you have very small sample sizes, like log n, if I'm not mistaken. Do you, if I reduce S, do I pay inversely in sample size?
Yeah, actually, we have not explored that. That's a very nice question. Yeah, I mean, obviously, there's a very simple thing that you can do where you just intervene at every node, and that is linearly many interventions. So we show that if you can intervene on constant fraction of the nodes, then you can do logarithmic many interventions. I don't know the trade-off in between. Yeah.
But most of your deduction was fairly local anyway, so it seems like it should just, like you have to hit everywhere, seem like.
Right. You need some kind, yeah, like a hitting set kind of structure to,
that would be inverse.
hit. Yeah. Yeah, I don't know the exact dependence, but yeah.
Can I follow up on this question?
Yeah.
In terms of like the first part where you just have, let's say, two variables, I think it's
Right.
really exciting that you know how to trade off between interventional and observational data. So if you can allow yourself soft interventions, you could just intervene on both. And it seems, at least from simulations, I think also Frederick has done that in the soft intervention setting, you should be able to actually reduce the number of samples as compared to hard interventions. Do you have any intuition, and have you looked at that? Like how soft interventions would actually even be better as compared to the do ones?
No, that's a great question. Yeah, so this is very recent work. We haven't actually had any chance to explore further. But yeah, we'll, yeah, let's talk.
Yeah, and for the structure learning and for the just a parameter learning would be really exciting to know.
Thanks.
This question's for Chris. Two questions, I guess. One question was on, so is the estimate actually at the end based on the randomization procedure produced, actually unbiased estimate of the treatment effect? And the second question is related to inference. So you briefly mentioned at the very end about the confidence interval construction being potentially conservative versus, I presume, compared to, let's say, a covariate adjusted one, or maybe even just a straight up Horvitz-Thompson kind of just without any covariates. So can you just comment on like that kind of practical, like I guess the inferential question. So suppose I optimize between the robustness and the efficient robustness and these characteristics, but what would the inferential characteristics look like? Because it seems like the talk was mainly focused on the MSE balancing, not so much in the inferential. Thank you.
Yeah, so that was a lot. Let me know if I don't get to one of your questions here. All very good. The first thing is that yes, this robustness, you know, okay, so first off, the very first question is you asked. We're using the Horvitz-Thompson estimator. Our design, we know the marginal probabilities of treatment. They're all like one half. You can modify that if you want. I didn't go into how, but you can modify that. So whenever you know the individual marginal probabilities of treatment, and whenever they're bounded away from 0 and 1, in this design-based setting here, the estimator is unbiased. So our design definitely satisfies that. So we're definitely having an unbiased estimator. That was your first question. The other questions, so yes, the robustness versus covariate balance, that's all thinking about mean squared error. Okay, and so I think that in general, and this is not a formal statement I'm making, but it's my experience that if you want to, design an experiment to make mean squared error of an estimator small, that's a related but generally different thing from making your confidence intervals very small. Unless you're willing to make some normal assumption, then it's the same thing, I think. So I actually don't know like what a general design satisfying robustness and covariate balance. I don't know what the like analog for robustness and covariate balance is for confidence intervals. You could do it for, we gave this sub-Gaussian result, which gives you tail bounds. And from those tail bounds, you can get confidence intervals, but those hold in finite samples. So they're going to be loose a lot of times. Whereas a normal approximation, it's exact in some appropriate limit, which usually feels reasonable in practice. So yeah, like our confidence intervals are larger than that you'd get if you made a normal, but you could make a normal approximation, which says the variance of your estimator is all that really matters for determining the width. If you use our design, the variance is small, if the outcomes are related to the covariates and if you've chosen to balance. So because you get increased precision with our design in certain cases, if you had a central limit theorem, that would carry over to like small confidence intervals in that way. Does that answer the question? I think I kind of just rambled around the things that you asked. Does that answer the question more or less?
Thank you.
Thanks.
I had a question.
Oh, sorry, go ahead.
Yeah, I had a question to Chris. So it seems that your design, your goal is to have the mean square error be bounded as a function of the approximation with respect to linear functions, right?
Yes, yes.
So if you generalize the class of linear functions to other classes of functions, are there interesting discrepancy problems which come out presenting it up that way?
Well, there are things we can do, yes. Are they interesting? That's up to debate. You can extend everything I've done to kernel methods. And so that's like a chapter in the dissertation that I have. It's not in the paper that we have on archive. I hope it'll be its own kind of paper once I flesh out some other details and stuff. But what we've done is we've said, let me tell you what that result looks like. We say, okay, the variance is of the Horvitz-Thompson estimator is bounded above by some ridge regression where you're looking over linear functions. There's a way to do a kernel trick in this Graham-Schmidt walk. It's the exact way you think it would work. And instead of a linear like ridge regression, you do a kernel ridge regression. So if you want to extend to non-linear function spaces, if you're willing to use kernels, pretty much everything works in the exact same way. There's like slight minor things you need to be careful of, but it's pretty much the exact same way. I think that interesting nonlinear functions could be like, what if it's a sparse linear function? Like there's some sparse linear function that's good. I don't know which one. That to me is, I have no idea what to do there. Yeah, I don't know. So there's but in terms of RKHS, not so interesting in the sense that the same methodology still works. Interesting that you can do that. Outside of RKHS, many open questions, I would say.
Thanks.
I can guess my questions.
Hi, Chris. Nice talk. So you mentioned that you want to think about the online version of the algorithm. And there is the self-balancing walk, which tries to solve the same problem in an online manner. Do you is there a concern why that is not appropriate, or is that, I know it has this extra root log factor or something. Is that the main reason, or there are some other reasons that you think it's not appropriate here?
There's one super main reason that it won't work, which is that, so you may reference this paper. I forget the author's exact names, but it's LSS, and it came out maybe a year or two ago, maybe a year ago. And I looked at it a lot, and they solve a discrepancy problem. So it's not this distributional thing, but they do distributional stuff. So it's not too far, to modify. The real problem is that their assignments, they allow for +1, -1, and 0, or +1, -1, and like 3, I think, or 2. So they don't, and it's a great paper. So let me not, I'm very excited by that paper. But in this context, it doesn't quite work because you can't have like someone just not be assigned to treatment, or it's a very odd thing. If you did that, it could very well like mess up the estimator that you have, and there's some care to be done there, but it is kind of weird to like just drop someone from
I
the
see.
study.
So actually, I have a follow-up work on that, and we can talk offline. That you don't have to do what they do. You can always assign, but you can always assign +-1. You don't have to do 0, and you can still do things. So we can talk
Wow.
offline.
Yeah, yes, I'm very curious. We'll talk offline. Yeah.
Question for Arnab. So for the observational study, I would assume that depends on how the observational study is, then that should factor into the complexity calculation too, right?
Sorry, what is the
The
context?
observational study, right? If it's not very informative about the possible causal effect,
Right.
then you will need a lot of them. So I don't know whether in your bound, whether you see that or not. Because there are many different observational studies could
Right.
be relevant, and some probably more helpful for causal inference than others. Do you see something like that in your theoretical work?
I think I don't fully understand the question. So your question is that if your observations don't reveal the causal structure?
Yeah, there's a different degree that the observational study can help you to review. For example, one observation that can have a lot more confounding factors than others.
Right.
Do you see something like that to characterize that in your theoretical
Yeah.
analysis?
I think, right. So, I mean, I guess you're referring to the first part of my talk, right? Where we were, yeah. So in order to generalize it to, I mean, more number of variables, or where you have more confounding, you would need, yeah, I mean, like, so you'd need a more detailed understanding of how observation, I mean, if you have more observations, I mean, you can, I mean, there's still a bottleneck. You do need interventions. You see that even in this simple example with 2 variables, but right, I mean, so there, yeah, I mean, you'd need to kind of, we still haven't looked at it at all, but like you'd need kind of the graphical structure of the different variables will definitely come into play when determining this trade-off between the number of observations and number of interventional samples. Yeah. Thanks.
Liam, I have a question for you. I'm not so familiar with the types of trees that you were describing, and so I was wondering. So my first reaction was, "Oh dear, this is going to explode the moment that I have a large state space. Never mind if I go continuous or something like that." So what I then was wondering is that, okay, firstly, I was thinking that, well, how do you think about a generalization conceptually of this to the continuous space, if at all, or you just, this is not going to work, that's completely hopeless? And then secondly, I was wondering to what extent this sort of representation relates to other representations, say, if you wanted to do this in terms of potential outcomes, for example. I don't know if you have something to say about that.
Yeah, so yeah, everything that we've been doing so far is in the discrete setting. And honestly, I think it's a really great question to consider what could be done in the continuous setting. But currently I have no thoughts on that question, but I think it's a really good one and worth exploring. Yeah, in terms of potential outcomes and other things, one, I think recently at the Stanford online causal inference seminar, I think Thomas Richardson was giving a talk about some recent work with maybe Jamie Rubin about models for, I can't remember what they're called, but they were a new family of models where they were using essentially augmented DAGs to explore like how you go about modeling potential outcomes and things like this. So I think it is worth sort of exploring how these CS trees relate to these other sort of context-specific models, and in particular that family. And perhaps from that perspective, we could see something like potential outcomes. I know also that in regards to computing potential outcomes, there's been some work within a group at Google DeepMind who's been using these stage tree methods to actually to model these things. So exploring the relation between how they've been looking at stage trees and how it might connect to this specific family of CS trees could shed some light on it, but I haven't thought about it so much so far. So thanks.
So this seems to be very orthogonal to somehow what we have heard, for example, in the morning, right, on the invariance principle, where we're looking at, what is causal is maybe should be something that is invariant to all of the different environments or all of the different contexts. Whereas you're looking at within a context, right, it could behave differently. So there seems to be like, it's exactly in the opposite direction. So how would you even connect to something like Chiara's talk in the morning, where, this is exactly what she's using, is this invariance to get at these causal effects?
Right. Yeah. I mean, I guess in some sense, maybe I don't quite get the question, but I guess in some sense, we are still using invariances to get at causal effects, but now we're doing it within the context. So to me, that's sort of the natural connection, but I'm not sure much beyond that, what you have in mind.
Yeah. And you could actually even more use like different kinds of environments within it.
Yeah, absolutely. That sounds completely worth it thinking about.
There's a question from Thomas. Thomas, I believe if you unmute, then because you're panelist, you can actually talk.
Can you hear me? Yeah, so I was just following off on Liam's comment. So that I think the graphs probably was single world intervention graphs. And I was going to add as a quick comment that I don't think I didn't mention it in the seminar, but we've given a little example in paper with Ilya Spitzer where we did something context specific, and we showed that you could get some identification results from context specific independence that you can't get, and this is for an ordinary intervention distribution, and we gave a kind of semi-plausible example as to how the context specific independence could arise. And one other comment, there's a paper by some authors from Finland, some of them at Jyväskylä, that also were using context-specific independence and had a kind of context-specific version of the do calculus. So I just throw that in there as well.
Yeah. So question for Chris. So I want to understand the Z when the dependence between the Z when you do this like trade-off between the robustness and the tolerance balancing. If my X is actually orthogonal like features, can you say something about what the Z is?
Yes. Yeah, so I didn't mention it too much, but we kind of know what Grandson walk does for certain input covariate vectors. So if your covariate vectors are orthogonal, then your augmented covariate vectors, no matter what phi you set, are still orthogonal, and balancing those turns out to be the Bernoulli design. So if you gave me, covariate vectors which were orthogonal, I think this is the question that you're asking. If you give me orthogonal covariate vectors, I run the algorithm, no matter what I set that trade-off to be, I will always get the Bernoulli design. And you might say, wait, how are we balancing robustness and covariate balance? Well, it turns out that in that setting, robustness is equal to covariate balance, because I can take an orthogonal transformation of your covariates, get the identity matrix. So like the covariance of Z is that operator norm is equal to the operator norm covariance X Z. You can just do an orthogonal transformation. So that's it. So there's some settings where there is a real trade-off. That's like most covariate vectors. But there are some weird ones like the orthogonal where there essentially is no trade-off. All the results still apply. They just become less interesting at that point.
Arnab, you said at the end you're also interested in looking at how you might learn the graph in the first place with and placing bounds on it. Can you say a little bit more about that? Because I was actually very curious about how that would go, you know, especially if we're sequencing independence tests and earlier choice or earlier decisions might influence what sort of subsequent tests we're doing. Can you, I realize it's an open problem that you mentioned, but I'd be curious to hear.
Yeah, I mean, right, as I said, I mean, even without interventions, learning the Markov equivalence class, understanding what is the sample complexity of learning the Markov equivalence class, graph Lysen, or an approximate Markov equivalence class, in the sense that the graph expresses a distribution which is close in some sense to the given distribution. That is still an open question. So with interventions, as far as I know, there really has not been any work. I mean, trying to understand this trade-off between the samples, observational samples and interventional samples that you need in order to discover a causal graph. I think we were just discussing with other people. I think this is a super interesting problem. Yeah, I mean, there are some trivial things you can say, like you can, of course, intervene on every node. And in that way, you can learn who the parents are. But doing everything in a computationally efficient way and also minimizing the number of interventions, this full trade-off is far from understood right now. Yeah.
Any other questions either? I would say let's thank our speakers and yeah, thank you very much. Are there any announcements from the organizers for tomorrow? Otherwise,
No, we'll just meet for coffee again at 9 a.m. and then at 9:30 we'll get started.
thank you all very much. Thank you.